Hi, thanks for the opportunity. So I'll talk about improving detection of radio signals, having spectral structures. I'm Pravir and I am postdoctoral fellow at Weizmann and working with Bonn. So we have seen examples of FRBs and the non-uniform nature of their spectra. So detection of radio signals from FRBs remains a challenge because of that non-uniform nature. This is typically due to interstellar scintillation, which is induced by propagation of radio waves through inhomogeneous medium. Then, apart from that, most FRBs are band limited, and it has been shown in the CHIME sample that there is a morphological differences among the FRBs. So the repeating FRBs are band limited compared to the apparently non-repeating FRBs. And there are more complicated frequency dependent intensity patterns. The current techniques of searching FRBs assume that there is uniform flux across the frequency. So what we do is we sum the signal in frequency and form a time series like that and do a match filtering to detect signals. But if the spectra is non-uniform, then there is a chance that when we average signal, that results in loss of sensitivity. And so one way to overcome this is by doing subband searching, by dividing into subbands. But and someone who has done lots of subband searching, like I spent my entire PhD doing subband searching, so I can say that that should be the optimal way to do things. So let's devise a detection statistic for this, and so the spectral model that we have. So we have the de-dispersed intensity as a function of frequency, and that can be thought of as a combination of the received signal in a background noise, and that background noise we can assume it as a Gaussian following normal distribution. We don't know about the signal because we don't know much about FRBs. We don't have a clear model of their received signal, but we do know that there is amplitude correlation between adjacent frequencies. So we can approximate it as a random walk or a Gaussian process. The noise here, which is the process noise, so that sigma eta, that is the correlation length of the signal. So if we have a smaller correlation length, if you have a smaller sigma eta, then the correlation length will be larger, and vice versa. So we are approaching this in a Markov model framework. So in this framework, the I's are the observed states which we are observing, and the A's are the hidden states or the unknown state of the model. So the idea is to estimate the hidden states given the observations. So to detect a signal, we do a hypothesis testing, and the most optimal test is the Newman-Pearson test or the NP test. So we are interested in the likelihood of the probabilities of the joint distribution of observing the signal intensities and with signal and without signal. That's the ratio we're interested in. And the H0 case is easy because there is no signal, and so the noise are not correlated, and that can be calculated easily. H1 is a bit tricky because we have to calculate this joint distribution of these probabilities. So we can disentangle these probabilities in terms of the hidden states, and by doing some prior estimates of the hidden state given previous observations, and by that way we can get the H1 as well. So we have the detection statistic, which is the log likelihood ratio, and in the end we just need to get these estimates of the E and V's, which are just the expectancy and the variance of the hidden state given all the previous observations. And it turns out that this is the well-known Kalman filter. So this is basically the estimating the next state given the current state prediction by multiplying the measurement residual with some factor, which we call the Kalman gain. So what we're doing is we have some prior estimate of the current hidden state. We then do the measurement and update the estimate, and then predict about the next state. And this way the chain progresses for the entire observation, and that way we ultimately get this log likelihood, which is the detection statistic, which we call the Kalman score. So in summary, what we are doing is we are marginalizing over all possible intensity curves given the observations for a given correlation length. So for implementation, what we do is we give a bunch of values for correlation length. For each correlation length, we calculate this statistic, we calculate the significance, and the one with the better significance is the correlation length that we are searching for, and that is the significance that we are looking for of the signal. So to get the significance, we compare the extreme event that we are looking for in some background noise, and there are multiple ways this can be done. But what we are doing is we are Monte Carlo simulating a bunch of Kalman scores for the given noise distribution, and approximating the tail of distribution. We are then comparing the desired. We are comparing the Kalman score of the signal that we're interested in the background of this distribution, and it turns out that this Kalman score is independent of any constant bias. So if you add any term to the whole spectrum, it doesn't matter, because Kalman score is not measuring the power; it is measuring the shape of the signal in the spectrum. So it can be used in together with the traditional power integration statistic, and both can be combined together to boost the signal to noise ratio of the event. It can also easily handle missing channels, because usually we have many channels affected due to RFIs, and those channels are either blanked out or removed from the observation. But our model can easily make a continuous approximation across those channels, and so it can handle several such channels in the data. So we apply this to real data. So these are the ASCAP detected FRBs. This is the dynamic spectrum, frequency versus time. Then there is this pulse profile, and you can see the pulse profiles are quite diverse. Some are very band limited, others are not. And here we compare the signal to noise ratio obtained using the traditional match filtering of the time series, and then the bottom is what we get from using the Kalman method as well. So we see that for these things that we get a huge boost in the signal to noise because this method significantly improves signal to noise for extreme spectral morphology. So in this case, we have like an improvement of a factor of 2.5. But for example, this one, this 210117, this is a featureless spectrum. It's a broadband emission. There is no feature in here, and we don't see any improvement here. So that's the basic idea behind this. But this is not what this Kalman detector is meant for, because these events are already well above the detection threshold. So we really don't need a Kalman improvement to detect these events. This already has a signal to noise of 27 or 24. So what we're interested is in looking the application of or the utility of this Kalman detector for events which are near or below the detection threshold of the instruments. So here we simulate events in the range of 6.5 to 10.5 signal to noise, and this we do by using the template of the ASCAP FRBs that have been detected so far, and we simulate 1,000 such events, and we try to see how much. So y-axis is the new improved signal to noise using the Kalman method, and x-axis is the traditional boxcar method, and we try to see how much improvement we can obtain. So for most FRBs, we don't see much improvement because they are broadband, and we really don't expect anything here. But for many FRBs which are band limited, we see huge boost in the signal to noise ratios. This blue region we are not interested in because these are already above the detection threshold. So let's say 8 is the detection threshold. We are already getting these events. But events which are below this detection threshold, which are in this orange region, we were missing these events. But using this improved signal noise statistic, we will be able to detect these events. So that's the idea behind this Kalman detector. And overall, in this exercise, we see improvements up to 200%, more than 200%, and a median gain of around 20%. So yeah, so that's the result. Right, but however, you have already figured it out that we need the burst spectrum in order to get the Kalman score. And in order to get the spectrum, we need to know the pulse profile ahead of the time. So is there a way to do it more optimally? So it turns out there is, and if we can devise a binary tree approach to, because the earlier Kalman equation that I showed you, it works in linear approach, it works in linear time. But if there is a binary tree approach, then we can possibly combine this with FGMT and calculate all the necessary statistics at the dispersion stage itself. So it turns out it can be done. There is this big integral that needs to be solved, and the integration, the Kalman statistic is more complicated now. It's in 2D Gaussians now, and so if we have, so we can start with pairs of channels. We can add their Kalman statistics together, and ultimately we can do this in a bottom-up approach, and ultimately we have those Kalman statistics for the whole spectrum. So this can be done, and this can be solved analytically, but it turns out that the number of operations that need to be performed is more computationally expensive. So at this stage, we are only recommending to use the linear Kalman filter. So the idea is that we use this Kalman detector at the post-processing stage. We detect events, we know the pulse profile, get the spectrum, and then get the Kalman SNR. So the utility would be that we can lower the detection threshold, get more candidates, but we have some extra information which can be used to get more combined significance. So yeah, that's it. And yeah, this information has largely been unused in FRB searching. So this opens up new avenues for FRB.
When you do the single class could be for the box car, do you use a binary process for the box car for the single class computation, or do you do it full bank?
Full bank.
Yeah. In that case, would it be reasonable to compare the single class you get from Kalman, which is the spectral information, full bank versus just using full bank?
Sorry, I didn't understand.
Would it be reasonable to compare the single class that you get when you get full bank process? Process when you do Kalman single noise, which actually uses spectral information.
Yes, but the Kalman is not using the power in the data. It is using only the spectral state. So both are not comparable. But since both are using independent source of information, they can be added together.
Okay.
So that's what we are doing. So we are adding the Kalman signal noise on top of what we already have. Yeah.
I have another question. What's the false alarm rate that you get if you do Kalman searching? Instead of doing this post-processing as a first blind search step, if you get any false alarm, like false alarm probability?
Yeah, because this is a detection statistic, so of course it will boost any signal that is present. RFI is also a signal, so okay. We'll have lots of candidates for that.
Any last question?
Is there any way that could potentially use this to identify narrowband RFI?
Sure. I mean, this is a detection statistic. Again, this is not a classifier, but one can use it to identify RFI. Yeah.